Welcome. Welcome to the panel discussion. We are talking about AI and resilience in dynamic environments. And I'm very happy to welcome Professor Olga Fink from the Intelligent Maintenance Systems at the ETH. Very happy to welcome Dr. Ilya Feige, the Director of AI at faculty.ai. And I'm very happy to welcome my colleague Grégoire Caro, chapter lead of data science in Zurich from Swiss Re. Starting the discussion is a bit complicated. You have seen all the talks. I haven't. I'm jumping in last minute. But let me at least give the speakers a short opportunity to introduce themselves. Keep it short so that we have time to discuss. But if you don't mind, I would like to start with Olga.
Sure. I'm Olga Fink. I'm assistant professor at ETH Zurich, and our research deals with developing intelligent algorithms for complex industrial and infrastructure systems. So what we're mainly interested in is in detecting these rare events, but also predicting how the system condition is going to evolve over time. And finally, also not just predicting, but also prescribing how the systems need to be operated in this dynamic environment. And I'm looking forward to the discussion and handing over to Ilya then.
Thank you.
Thank you very much. Yeah, my name is Ilya. Nice to meet you all. I'm Director of AI at Faculty. I look after our research and development, and one of the main focus areas is the kind of topic of AI safety, or at least that's sort of the term we use. So certainly related to this discussion, things like explaining AI systems and ensuring their robustness, for example. And Faculty is a British artificial intelligence company.
Thank you, Ilya.
No problem.
Yeah, you wanted to hand over to Grégoire.
So I take over then. Happy to introduce myself. So Grégoire Caro. I've been working at Swiss Re for 7 years now. And I lead the data science chapter of the chapter of data scientists based in Zurich. We work on very different projects with all business units, with property and casualty, with life and health, and also with corporate solutions, our direct corporate insurer, mostly on structured data, but not only. And every time it rotates around better understanding the risk. So a bit similar to what Actuary does, but leveraging exotic data sets. I'm thinking of geospatial data, electronic health records, but sometimes as well, vessels track data, and so on and so forth. So quite diverse.
Thank you, Greg. Good. Let's get the discussion started, and maybe we start at a point that is clearly at the heart of the discussion at this point in time. We all seen the pandemic changes everything. At the same time, while machine learning is a wonderful thing, it has that one little problem that it can only learn from the past. So in this situation, when everything changes, can we still use ML, or is ML doomed to fail because maybe the past doesn't really repeat itself? I would like to get started with Ilya, and then you guys jump in as you want.
Thanks. Yeah, I mean, I don't have a kind of silver bullet, but maybe just a useful framework is just to say that, like, does the past repeat itself? Yes, sometimes in some contexts, and is using this stationarity assumption where your training data comes from the same distribution as your assumed future data. Sometimes that's a terrible assumption. So something like, do people go to the cinema more on a Saturday than a Wednesday? Probably like a good signal to learn from and to apply to the future. But like, is the climate crisis, how is the climate crisis going to affect national infrastructure? Probably not. Probably not a good question. So just like one, I think just a useful sort of analogy at the risk of anthropomorphizing is like human intelligence has, or at least this like kind of common heuristic framework of like type 1 and type 2 decision making. So you're like heuristic, intuitive, touch the stove, it's hot, pull away. And you're like more rational, what degree should I do at university type decisions. And like that serves us very well. We use machine learning, whatever the equivalent of machine learning, to an incredible degree of like performance and effectiveness in our lives, type 1 thinking, but not exclusively. And surely that should be the same for AI and how organizations use AI. The things that are rote, definitely use machine learning, exploit it. It's great. The things that are not, like, don't, just sort of use other methods there. So what others think?
So I don't know if I should go to next, but actually we have 2 recipes how we are dealing with the type of events that we are detecting or predicting. And one of the recipes is that we are not trying to learn the event that we actually would like to detect, because they are so rare and it's basically impossible even to learn that or to learn the specific pattern. What we are then trying rather to learn is the normal system condition, and even the normal system condition obviously evolves over time. But then our goal is not for these rare events, not to predict them, but rather to monitor and then perform early detection. So this is one of the recipes for this for these rare events. And the other recipe that we are applying is when we are able to induce some physical information in the models, then obviously we need less data to train the algorithm. We're able then also to generalize better and possibly also extrapolate a bit depending on how much extrapolation we will need.
Maybe what I'm hearing is you're giving up a little. Identify when to use ML, when can we not use ML. Going back to early detection, is this maybe in addition to these things, which are obviously good strategies, do we maybe see also a rise of agent-based systems? That going back to what you said, Ilya, type 1, type 2 decisions, maybe we cannot predict on a global scale what the system is doing, but maybe we can try to predict what a single rational actor would do, and then a rational actor is obviously an approximation what humans would do, but then maybe get an idea what the overall system would do.
I could certainly comment on that and agree, but wondering if others have interesting things to share. Well, basically, what I would say is yes, exactly. So agent-based modeling or sort of more mechanistic modeling is a good alternative to machine learning in these instances. And I'm sure many people did not catch my talk this morning on the NHS COVID response, where like the sort of next 3 weeks were predicted using statistical models. But we actually also, in order to try to reason about what might happen in 6 months, could not use statistical models at all. And so had to use agent-based simulations for these kind of older school epidemiological models, just to get an idea of what scenarios might look like.
Okay.
So maybe just to complement, because you're mentioning we are giving up on ML for rare event detection. We're actually using ML to learn the healthy conditions. So we're not giving up on that, but we are kind of adjusting that to the conditions that we're using it for. But also, thanks for pointing out this multi-agent systems. And it's not just multi-agent systems, it's partly even hierarchical multi-agent systems. And we're also looking into that, particularly for the cases where we have the systems of systems performance, and where we are not just looking into a single component, but partly at the networks of components. And this is where we need to look into the bigger picture, but also on how the agents are reaching decisions between each other. So that's one of the directions. But obviously, we are not giving completely up. But we're trying to find solutions for this lack of data or lack of representative data, and how to adjust it to and still being able to apply and solve the problems that we're seeking to solve.
Maybe I can build a bit on that actually. So I think when it comes to rare events at Swiss Re, we think, for instance, of natural catastrophe. It's one of the largest we try to cover. And here it's quite clear that the supervised algorithm, say for a tsunami model, will not work, even though if we had 100 years of data. So as such a way, yes, we did give up on machine learning for this one. And here we fully fall back on simulations approach, so where we feed in explicit understanding, physical understanding of the natural event we try to model, basically of the peril we try to model, be it a tsunami or a landslide layer or a drought, and so on and so forth. When it comes to the beauty as well of this simulation is that we can easily feed, again, expert-driven, so effects like the global warming, so that's great. When it comes to the other types of rare events, say so what we call man-made, things like, I don't know, a total loss of a ship, for instance, or an industry or bridge collapsing, we do try ML from time to time, but here we need to be, so we don't try to predict the event. I think that's the beauty. We're happy only when we can just classify low risk and high risk. So that way it's hard to prove us wrong, because if I say it's a 1 in a million risk or 1 in a 10,000 risk, it's hard to prove that my forecast is wrong, basically. And that makes it also much easier. There we also tried, so sometimes it does work when it's when the systems underneath are simple enough. Otherwise, we need to go back as well to a hierarchical model where we can feed in even more expert-driven views and expert mechanisms. So I think it's also a bit of a spectrum between full simulation, a little machine learning, full physics almost, to something almost full supervised learning.
Thanks, Greg. Sorry for being a bit provocative. I'm a bit sad to hear, as a computer scientist, I'm a bit sad to hear that we're falling back to physics, but what can you do? But talking about these rare events, and you mentioned it, Greg, as a Swiss Re, as a company, we are super interested, obviously, in these super rare natural catastrophes and things like that, and we're collecting that data basically since 150 years. But at the same time, well, we try to predict things like return periods, like risk. How often does that happen? What do we have to expect? But climate change is one thing. There are many other aspects that are changing and evolving over time. How do we tackle the problem of adjusting what we've learned from the past with changing circumstances in the future? Maybe Greg, because you started the topic, maybe you can give it a go.
I think that's what makes it hard. That one NatCat observations does not validate or invalidate any sort of risk model. So you need to go back more to the fundamentals. We do talk about, as you said, we would talk for a given hurricane of a 1 in 100 years event or a 1 in 50 years event. So that's how we calibrate it then. And later on, there is a feedback loop to revise the assumptions, but by all means, it's not, unlike with a supervised learning, it's not one event which are as such, which is going to change the technique underneath. Because it is so rare, basically, we cannot draw a conclusion. So it's a bit maybe a disappointing answer to you, but I think that's in the essence of the business to be careful with this. I don't know, maybe the others, you have a different view on this feedback loop from rare event to the observed window to the risk.
Yeah, maybe I can add, but not from the rare event, but what we are typically with complex systems, what we are dealing with is that the operating conditions are also evolving over time. So even if we use the training data set that was representative at the point of time when we train the model, then later on the machines may be operated under different conditions. So then we'll still need to adjust the models to the changing conditions. And this is on the one hand, where we can apply continuous learning to that, so adapting the models while the data actually evolves. And depending on how novel it is, we could possibly even apply domain adaptation. So that kind of using the experience, for example, of other units and transfer it to the unit that we're now would like to observe. So there are different approaches, again, also to adjust to kind of to new conditions, to evolving conditions. But for us, it's not that much about kind of feeding back the rare events, because normally this is what we would like to detect, and obviously we are validating if it's possible to detect them or not, if the models are suitable for that, and then recalibrating possibly a bit. But for us, it's rather used to validate if the approaches are suitable.
Thanks for that. Talking about this, we have a lot of models that take really exactly what's the distribution that we see, and we can predict within that distribution that we trained upon. On the other hand, there are, for example, simple linear models where if I have some distribution that may not cover everything I might want to predict in the future, but at least I get the mechanism for, I can at least in theory predict things that are outside of the observed training distribution. So in a sense, we see a certain physical approach in that we model the mechanism and then can conclude into areas that we haven't trained on. Do we see maybe also a rise, or how do you see that this putting together physical approaches with machine learning approaches to solve exactly this problem of going into the future, going into the unknown, going beyond the distribution that we see in the training set? Maybe Olga, if you would like to start, but anybody else?
So recently there have been one of the directions, one of the evolving directions has been, for example, the physics-informed neural networks, but also various approaches that are trying to integrate some of the physical prior knowledge into deep learning models to close some of the gaps. And that reduces for us the dependency of training data quite significantly. That on the one hand, we can use partly the simulated data, but then also to adjust to new conditions as well. So it has been even one of the kind of emerging AI topics, and so several companies are also trying to integrate that, because on the one hand, it really provides also the basis to understand the underlying systems and the underlying processes in a better way, but also to get the engineers back into the modeling and integrate their prior knowledge into the models. And yes, it provides us better possibilities to extrapolate beyond what we have actually observed in the training data. So it's still evolving direction that has become quite popular, particularly in the last maybe 1 or 2 years. So on this AI hype cycle, so it's kind of on this emerging side, it is quite a promising direction to go
in. You look like you want to say something.
Are you looking at me?
I'm just saying, maybe I'm misrepresenting you.
No, I could certainly jump in. Yeah, well, just to say, I agree completely with Olga. And one, just like sort of shifting a little bit, shifting away from sort of tail events or natural disasters or physics to like how a company's supply chain works or something. Like we don't have fundamental like scientific models for these things, but the kind of current discussion is still incredibly relevant, and it's definitely the way that we faculty are thinking about these problems. So if you imagine like taking a value chain within an organization, like supply chain. So I need to like source components, I need to put it through my factory, I need to then take the finished goods, put them into distribution centers to meet demand. There is like a fairly like tractable causal graph that you can just write down, not because you know like the fundamental laws of nature, like what causes landslides, but because you kind of are in control of a bunch of the steps because it's your company. you can tell people like to behave in a particular way. And so then you can use statistical models to sort of forecast demand. You can use mechanistic models to just describe how your factory works. And you can use machine learning models at the nodes of these causal graphs. So something like, if I put this many goods in, raw materials, the like quality distribution looks like this. And then when you have like big shifts, because you have the causal graph approximately written down well, the individual machine learning models like don't go out of distribution anywhere near as quickly. They're sort of simpler models. You can understand them well, and you can use the monitoring techniques that Olga was referring to just know when they kind of go off manifold or out of distribution, or however you want to call it. So yeah, this sort of approach I think is ultra relevant, even when the causal graph is like not scientifically motivated for sort of generic businesses.
Sounds like me that sounds to me a little bit like we are moving back from the explosion of the black box models that can do everything, but we don't really know what's happening inside, back to a situation where we actually need to understand the process and try to really put our hands on modeling. When you talk about causal graphs, what can Bayesian probabilistic modeling contribute to the problem?
I'm sort of going to steal that. I assume you're asking me just because I did my talk on this earlier today. So for the causal graph, like for the causal modeling, this sort of picture of the graph where you get the sort of mechanisms, like you make the mechanisms explicit and then you let the machine learning models like live in sort of smaller domains. You could do that with or without Bayesian methods. However, when you try to like put this causal graph together into a system that you can like optimize or reason about or do scenario planning on, or all the things a business wants to do, right? A business wants to like make sure that there's less than a 2.5% chance that their customers don't get the product they order when they order or something. Some like high level strategic goal. Anything like that, these are basically just like composition of probability distribution type questions. So I would claim that all the models in this graph need to be probabilistic. So the demand models, the kind of forecasts, if you want to do scenario planning, you can use different priors, or you can use just the different credibility intervals within the posterior of a forecast. But also if you want to like optimize it, so subject to 2.5% chance of stock out, I want to, minimize my inventory to have more working capital, or just think like maximize profit, right? Usually it's a little more subtle than that, but these are all like integrals over probability distributions. And if you don't get those right, like there's actually some kind of theorems that say you will like have a biased estimate of the optimal solution because the max is like non-convex or something. There's just sort of basic mathematical results. So totally need Bayesian methods, I would claim anyway, though maybe you guys can jump in and disagree if you do.
Actually, I would like to comment on your comment that you said about turning from black box models to more physics-based models. And I think it's what we actually see is that in the fields where deep learning has been really flourishing, that's computer vision, natural language processing. So in those fields, black box models have been prospering and are providing very good results. But in the fields where we don't have either sufficient data or where we already have physical models that could bridge parts of the gaps, this is where we see the development. That's particularly engineering and science, where the two domains could benefit from each other. And these are also the fields where we did not see that much development kind of in the field of applying AI, or where AI was really struggling due to this lack of data, but also due to the explainability, due to the or lack of explainability, but also due to the lack of extrapolation abilities. And this is where we need to adjust the AI models, or bring them also to the applications and adjust them to the application fields. And this is where we will probably see also in the future kind of probably having a mix of the two and benefiting from the two directions.
leading on that. I think it's also the regulator asking for transparency and fairness in the context of AI. So for at least for insurance purposes, so it's being developed more and more in these techniques. And as you said, I think it was a bit neglected over the last decade.
Thanks for that. A short organizational comment. I'm slightly confused because I see we just got another 15 minutes. I'm happy to take those 15 minutes. I have a lot of questions for you guys. So unless somebody interrupts me from the outside, I just keep this going. Because I think it's super interesting, and Olga, you mentioned the scarcity of data, and we tackled the problem a little bit and mentioned a couple of things. But in those situations, how do you overcome the problem of data scarcity?
Well, probably in our context, what we typically have lack of is particularly labeled data. And so, for example, we do have quite a lot of data on normal operating conditions, and these are typically not the ones that we would like to predict or to detect. We do have lack of labeled samples, and we're trying to overcome this by learning just the healthy conditions and kind of relying on it. And then we are not dependent on learning the specific features or the specific patterns of the events that we're interested in, and then also going in the direction of unsupervised learning, of trying to adjust to these conditions, but then still trying to make it adjustable or transferable to other conditions, or to other units or to other operating conditions. So that we are looking into which experience do those systems have, and how can other systems that are now operating in a bit similar way benefit from those operation experience, so that even if we are taking into operation new systems, that we can still transfer the models to other units of the fleet or to new operating conditions. So that we are trying to use the data as much as possible between different units, between different operating conditions, without relying on the labeled data.
We talked a little bit about this. We need to understand the process. We need to model the processes, and Ilya, you elaborated a little bit on the causal graphs and constructing these things. From my perspective, I mean, it's always good to understand what you're trying to model, but on the other hand, our understanding is always flawed. It's always biased. So when we construct physical models, when we construct causal graphs and things like this, how do we avoid that we are not just making a mistake and basically setting up the model for failure, because the underlying construction that we put in there, our assumptions of how the process works, is just plain wrong. Whoever wants to jump.
I can start, but I will start with saying that it's really hard. So if I interpret your question correctly as sort of a causal discovery question, so going from some complex system to the causal graph that is right. If you have the correct causal graph, it's kind of like you're in very good shape. Then you're in this world that I described earlier, where you've just got a bunch of simple models, and if you get them roughly right, and even if you don't, you can just compute their robustness and know when they shouldn't be trusted and everything. You're in good shape. But if you get the causal graph wrong, then you could have a bunch of good models that sort of come together into a system that is highly biased. So like the classic thing, the classic things to do is to sort of experiment and to experiment in the sense of like interventions, or think like A/B tests or whatever, in order to prove that your causal graph is right or wrong. But those like experimentation, which I think is a somewhat of an understudied or underrepresented field in kind of within machine learning, is time consuming. It can't always be done. for like rare event reasons or for like ethical reasons in things like healthcare and so on. So it's really hard.
I can maybe complement not on causal graphs, but rather on physical systems. Usually we are not completely wrong. Usually we do have, due to prior knowledge, to prior experience, we do have some understanding on the underlying processes. But the models will never be complete. And the question is, what's really the gap between what we are able to model and what we are actually observing? And this is where machine learning can help us to complement or to bridge this gap of what we're not able to model. And this is partly where the beauty of machine learning is actually coming in. If model, we're trying to learn this gap and then complement of the part that we're able to model. So that's one of the could be one of the answers. And one of the additional answers is to monitor the uncertainty of the predictions. So if then, and this is also going the direction what Ilya has been presenting. So not just to have the point estimate, but really also the uncertainty of the prediction, because if the uncertainty increases, or if the uncertainty is really high, then in this case, this is really an indicator not to trust the model in this input region, and possibly to divert to something else or to add additional information. Or to retrain the model. So whichever recipes are possible for us, but really not just relying on the point estimate, but also taking the uncertainty of the predictions into consideration.
Provocative question, because physical models, in a sense, you can also formulate them as a causal graph, and graphs at least make it easier for me to understand. Can you learn the causal graph? Because you have things that happen or might not happen. You move distributions between nodes, but the question in that causal graph is, where are the links? Which nodes are connected to each other? Which directions do these links have? Can we learn that?
I'm happy to take this. The answer is sort of no. There's a field called causal discovery that does this. So you can learn the causal graph like up to a potentially large equivalence class of all possible causal graphs that are consistent with the data you have, and like practically speaking, it's quite rare that the equivalence class is small enough that it sort of narrows it down to being confident about a given causal graph. So usually, if you're totally ignorant about the system, so I'm not talking about physical systems where humanity has been doing experiments learning the causal graph for like centuries. I'm talking about like, I've got a marketing team that's like trying to interact with customers and I want to understand how their purchasing behavior or something. Like usually you just have to do experiment after experiment after experiment, just like the scientific method does to understand the causal graphs of nature, in order to beat down the like equivalence class of possible causal graphs that are consistent with the data.
Okay. Sorry for that excursus. That was more a personal question than anything else. But getting back on track and also closing in on the end. What kind of developments do you guys see in the near future that predictive analytics will struggle with, and maybe also solutions? How can we cope with that? Maybe we do the full round, starting with Grégoire.
So I think Uwe, one in the near future for sure, there are many models that will need to be fixed because they rely on the longitudinal data approach with, maybe 5 years moving window, for instance. And the COVID has really impacted all the distributions and so on. So that would be basically the short-term challenge I can think of to adjust all the models. I'm thinking, for instance, we had a model around flight delays. So obviously we had maybe a full year of data where the prior distribution has fully changed. And the current model structure basically will not be able to capture it properly. So that would be the near future development that I can think of, to find either external factors to cope with these developments explicitly, knowing that now we're maybe getting back to the data, to the same data structure as before, or when we can actually afford it, for instance, in the EHR data to even remove 1 year of data, for instance.
Okay.
And I hand over to Ilya, for instance.
Thanks, Grégoire. That is definitely the right answer to the question of what like near-term developments will predictive analytics struggle with. Like my experience is like basically every company in the economy that uses machine learning, especially like I want to predict how much demand I'm going to have in the next 6 months, is sort of panicking that right now the environment is just totally different than it has been historically, and last year was totally different as well. So it's like new regime, the new regime, the new regime. So that is definitely a major challenge for predictive analytics. I think there's, it might be useful to kind of split how to deal with it in two. One, the discussion that we've mostly been having around like get the overall complex system model better, so that you can actually respond to shocks and so on, and sort of understand tail events and so on. But there is another approach, which is sort of very, very mundane. It's just get your iteration loops shorter. So if a business plans on a 6-month timescale, they can respond in 6 months. So a shock hits and they're just going to be wrong for 6 months. If they can get their sort of like operational timescales down, through which one of the main methods to do that is automation, data analytics, et cetera itself, then maybe you only need to predict 2 months out rather than 12 months now, because you can actually be much more agile. So becoming a more resilient organization, can kind of bridge the gap a little bit, because then your models only need to be good for a shorter period of time, or they need to predict an easier target, say. So that's a whole kind of another angle to solving the problem.
Thanks, Ilya. Olga, what's your perspective?
Yeah, some of the promising directions will obviously be making the models better generalizable and better scalable. So if not just making them applicable to very specific conditions, but really to enable them to be transferable between different conditions and kind of to benefit from the prior experiences. So that's going in the direction of transferability, but also using the prior knowledge and some of the models and complement the two worlds, and also making them better interpretable. That's also one of the struggles, kind of to get everyone involved. You then also need to provide better interpretations and also provide better insights on how these predictions have been achieved and what has actually driven those predictions, or possibly even giving insights into the underlying systems and underlying processes, which may give them more trust and more explainability to those.
Thanks a lot for your perspective here. We are closing in on the end. Any closing remarks from any of you guys? Good. Greg?
No, I just wanted to thank my two other colleagues, because I learned a lot, I think. So I took plenty of notes, and I look forward to discuss them with the team.
That is exactly also what I wanted to do. Thanks a lot to all of you. I did learn a lot, and I shamelessly also used that to ask some personal questions. So sorry for that. I hope you guys enjoyed it. I hope the audience enjoyed it. I also am obliged to tell you that we are going to the lunch break now, and we'll be back at 15:30 CET. So thanks to all the speakers here. Thanks a lot for this super interesting discussion, and enjoy your lunch, and be back at 15:30.
Thanks a lot to you and to the others. Bye.
Thank you.
Thanks. Bye-bye.